Okay, welcome back. Here's part two. The Student Services Office did a survey of 500 students in which they asked if the student is part-time or full-time. Another question asked whether the student was a transfer student. The results follow. Here we have a table with some survey information, and basically we have to calculate the probability of different things that would particularly occur. Part A here says if a student is selected at random from this group, find the probability that the student is a transfer student. Well, look at your total transfer students here. That's this column, 270 out of the total of 500. So it would be 270 out of 500. And then you would simply, you can reduce it, just change to a decimal, whatever. Part B, probability that a student is part-time. So here, total part-time students, 210 out of 500. Here, and notice I can bypass this and just read this. It says the same thing. The probability of the transfer student and their part-time. This means and. That's a symbol. So transfer student part-time is going to be 100 out of a total of 500. Part D says transfer student. This line means given. That's conditional probability. So there's a transfer student given that the student is part-time. So I'm only looking at part-time students now. So part-time students here, 210. Transfer, 100. So it's 100 out of 210. Alright, part E. Same thing but opposite. Part-time given transfer student. So we're only looking at transfer students. So total my sample space is 270. So it's going to be 100 out of 270 for that one. And here, are the events part-time and transfer independent? What does that mean? That means you have to do two sides of this. You have to look for the probability that an event is part-time. Is that equal to the probability that the event is part-time given that you're choosing a transfer student? And we also have to do the other side. We have to look at the probability that it's transfer student. Is that equal to the probability that it's transfer student given part-time? And if they're equal, then you say they're independent. If they're not equal, you say they're dependent. And let's go down here to the solution instead of writing that out. Here it says the definition of independent is so forth and so on. Here we had to find the probability that the student is part-time. Is that equal to the probability of part-time given a transfer student? If they're equal, then we say yes. If they're not, then they say no. We have to do both sides. But basically, if one side fails, you're done. So here, this one, it's already not equal, so we would be done. But here, we could also test the other side, but it's also no. So, and that's it. Part G says, are the events part-time and transfer mutually exclusive? That simply means, mutually exclusive means two events that cannot occur at the same time. And if we go down here, if it's in this table here, most likely it's not going to be mutually exclusive. Not all the time, but most of the time it's not. But these two events, transfer and part-time, they are not mutually exclusive. So, all right. And here, this is a good point. It says their events, when you find their intersection, it must be 0. And again, like I said, if it's in this table form, they're going to be, most of the time, it's going to be mutually exclusive. So, all right, number 11. A shipment of 40 television sets contain 3 defective units. How many ways can a vending company buy 5 of these units? This is going to be a combination problem. Let's think about it. How many are not how many are not defective? Well, it's 37. And it says how many ways can the vending company buy 5? So out of 37, I want to choose 5 of them, and how many ways can that occur? So basically that's a combination problem. Now scroll down here, that's out of 37. Here we're going to choose 5, and I would use your software to do that calculation. And on to part 3.